You've probably seen this headline everywhere by now. Quantum memory defeats traditional RAM. Scientists shocked. Your computer is about to change forever. It's the same storyline we keep seeing with quantum breakthroughs, and it follows the exact same playbook every single time. And every single time, the reality is wildly different from what you read. This has been happening for years. Every month, another headline. Every quarter, another breakthrough that's supposed to revolutionize computing. And every time you dig into what actually happened, you find something very different from what the headline claims. This pattern is so predictable that you can almost set your watch by it. Someone does legitimate research. A real scientific advance happens. A team publishes their findings in a peer-reviewed journal. And then, somewhere between the lab and your social media feed, the story transforms. The nuance disappears. The caveats vanish. The limitations get edited out. The timeframes get compressed. What remains is a headline so sensational that it bears almost no resemblance to what the researchers actually discovered. This is that story, and once you understand what really happened, you'll start seeing this playbook everywhere in quantum computing coverage. It's not unique. It's not an accident. It's systematic. It's how quantum hype works, and understanding why it works reveals something important about how science gets communicated in the 21st century. The headline in question came from recent research at Zhejiang University. A team of scientists did something genuinely impressive with quantum random access memory architecture. They demonstrated new approaches to one of the most stubborn problems in quantum computing. But the way this breakthrough got packaged and sold to the world transformed it into something it absolutely is not. The narrative became clear and simple. Quantum memory defeated traditional RAM. Game over. Classical computing is obsolete. The future is here. Except that's not what happened. Not even close. And the gap between what this headline claims and what the research actually shows is so enormous that it fundamentally changes how you should think about quantum breakthroughs. It also reveals something crucial about how these stories work, why they spread the way they do, and what makes people believe them so readily. Let's start with the most obvious problem. Quantum memory and traditional RAM are not competitors. They're not even in the same category. When you read that quantum memory defeated traditional RAM, you're reading something that makes as much sense as saying a radar system defeated the human eye. One doesn't replace the other. They solve completely different problems in completely different contexts. But that distinction is boring. That distinction doesn't make headlines explode across social media. The actual research that sparked this firestorm involved something called quantum random access memory, or QRAM. Not quantum memory, QRAM. This is a crucial distinction that almost nobody talks about when they share the headline. QRAM is designed to solve a very specific problem in quantum computing. It's designed to help quantum computers access classical data efficiently. That's it. It's not meant to replace the RAM in your laptop or your phone or your gaming PC. It's not meant to revolutionize how human beings store information on personal devices. It's not competing with DDR5 memory modules or the RAM in your data center. It's not trying to replace anything in the classical computing world. What QRAM does is enable a quantum computer to query classical information that's stored in conventional binary format. A quantum computer operates on qubits, which can exist in a state called superposition, where they are simultaneously 0 and 1. Classical information is stored as straightforward zeros and ones. The problem is that quantum computers are terrible at accessing classical data in the classical way. If you try to load a massive data set into a quantum computer by feeding it through a classical interface, the quantum computer becomes a bottleneck. Even the fastest quantum processor imaginable would be slowed down to nothing if it had to sequentially process enormous amounts of classical data one item at a time. Think about it this way. Imagine you have a quantum computer with thousands of qubits all in superposition, all ready to process information in parallel across exponential numbers of states simultaneously. That's the power of quantum computing. That's the potential. But that potential only works if you can get classical information into the quantum computer efficiently. If you have to load that classical information one piece at a time, one classical bit at a time, you've completely eliminated the speedup. You've turned an exponential advantage into a sequential bottleneck. The quantum computer becomes not more powerful, but less powerful than a classical computer handling the same problem. This is the data loading problem. This is the challenge that QRAM is trying to solve. This is where QRAM comes in. It's a specialized quantum architecture that allows quantum computers to access information in superposition. Instead of querying classical data, one address at a time, a CRAM system can query multiple addresses simultaneously by putting the address register into superposition. This theoretical speedup could be essential for quantum algorithms that need to process large classical datasets. Without it, many of the quantum algorithms that researchers have designed simply cannot achieve the speedup that quantum computing promises. Grover's algorithm for database search assumes you can access data in superposition. Quantum machine learning algorithms assume you can load training data efficiently. Quantum simulation of chemical systems assumes you can prepare initial conditions without bottlenecks. All of these depend on having QRAM or something functionally equivalent. That's what the Zhejiang research was actually about. In March of 2026, a team led by researchers at Zhejiang University experimentally demonstrated a QRAM architecture on a superconducting quantum processor. They built working systems that addressed 4 classical bits and 8 classical bits. The results showed query fidelities of 81% for the 4-bit system and 60% for the 8-bit system. These are real achievements. This is genuine scientific progress. The researchers successfully implemented something that many people thought would be far more difficult than it turned out to be. They published their work in Nature Physics, one of the top physics journals in the world. This wasn't a preprint on an archive. This was peer-reviewed research that went through rigorous scrutiny from other experts in the field. But here's where we need to talk about what these numbers actually mean. Because when you see 81% and 60%, your brain might automatically think, that sounds pretty good. That sounds like something is mostly working. That sounds like a functioning technology ready to change the world. Except in quantum computing, fidelity numbers tell a very different story. 81% is still very far from what you need for a practical system. 60% is even further away. These aren't victory margins. These are proof of concept demonstrations. This is the moment when researchers show that something is possible in principle, but solving it in principle is radically different from solving it in practice. Think about what 60% fidelity actually means. It means that if you run the same operation 10 times, 6 of those times you get the right answer, and 4 times you get the wrong answer. That's not something you can use in a practical system. You can't build a computer where 40% of your operations are producing incorrect results. You can't scale that to larger and more complex calculations. The errors would completely overwhelm any useful computation. For QRAM to be useful in a real quantum computer, you'd need the fidelity to be 95% or higher, ideally above 99%. The Zhejiang team is currently operating at 1/10 the fidelity you'd actually need. The team was explicit about this. They described their own results as remaining at the proof of concept stage. Significant challenges in scaling, accuracy, error correction, and hardware development all stand between this demonstration and any real-world application. The researchers themselves were clear about the limitations. They're scientists. They understand the gap between proof of concept and practical technology. But again, limitations don't make for viral headlines. Limitations don't make people excited. So, somewhere in the process of turning this technical paper into content for the masses, all of those limitations got stripped away. The caveats disappeared. What remained was the sensational angle. Quantum defeated classical. The real story here involves understanding what quantum memory and classical RAM actually are, and why the comparison makes no sense. Quantum memory as a concept refers to systems that store quantum information itself, that preserve the fragile quantum states called qubits. This is incredibly difficult because quantum states are delicate. They collapse easily. They decohere rapidly. If you try to store a qubit in a quantum memory system, you've got roughly 100 milliseconds before the quantum information degrades. Not seconds, not minutes, milliseconds. 1/10 of a second. That's the fundamental constraint. That's what you're working with. Some quantum memory systems do better than that now. The Caltech team demonstrated a breakthrough using mechanical quantum memory that extended quantum storage times 30 times longer than previous methods. Even with that enormous improvement, we're still talking about time frames that are vanishingly short from a practical perspective. Classical RAM is completely different. It can persist indefinitely. You can shut down your computer, leave it off for a year, turn it back on, and the data in RAM will still be there waiting for you. The bits have perfect fidelity. The data hasn't degraded. The information is intact. Quantum memory can't do that. The physics don't allow it. The superposition that makes quantum computing possible is also the thing that makes quantum information so fragile. You're fighting against the very laws of physics that make quantum computing work in the first place. Superposition is a resource. It's what gives quantum computers their power. But it's also a liability. The moment you stop actively protecting that superposition, it collapses. The quantum advantage vanishes. The information becomes classical again. There's another crucial difference that the headline doesn't mention. Reading quantum data destroys it. When you measure a quantum state, you force it to collapse into either 0 or 1. The superposition vanishes. You can only read the data once. After that, all of the quantum information that was stored in that qubit is gone. You now have a classical bit. You have 0 or 1. You've lost the quantum advantage. Classical RAM doesn't work like this. You can read the same memory location thousands of times. The data persists. It doesn't change. It doesn't get consumed by the act of reading it. These aren't minor technical differences. These are fundamental distinctions in how quantum and classical systems work. They're not in competition. They're not rivals. They're different tools for different jobs. The headline that says quantum memory defeats traditional RAM is like saying a hammer defeats a screwdriver. The comparison doesn't make sense because they're not solving the same problem. But this misunderstanding runs deep in how these stories get told. The Zhejiang research wasn't about quantum memory defeating RAM at all. It was about a specialized type of quantum architecture called QRAM, which helps quantum computers interact with classical data. The team demonstrated that you could build a QRAM system using a bucket brigade architecture. The bucket brigade design is named for the way old fire brigades would pass buckets of water from hand to hand. In a quantum context, it means that quantum gates pass quantum states through a series of steps to route the information to the correct location. The demonstration used superconducting qubits, which are the most mature quantum computing platform we have right now. The researchers showed that the bucket brigade QRAM architecture could be implemented on these devices with reasonable fidelity. This is important because it suggests a practical path toward building QRAM systems. But implementation at low fidelity in a proof of concept stage is still very far from having a technology ready to use in the real world. The researchers would need to scale this up dramatically. They'd need to improve the fidelity significantly. They'd need to solve the error correction problem. They'd need to demonstrate that this works reliably with larger numbers of qubits and larger datasets. None of this is simple. None of this is fast. The fact that they did it at all is genuinely impressive. But impressive in a laboratory is not the same as ready for deployment. There's usually a very long bridge between proof of concept and practical application. That bridge requires solving engineering problems that are often far more difficult than the original physics problem. That bridge requires building hardware that doesn't currently exist. That bridge requires developing error correction schemes that can function reliably with imperfect components. And that's before you even get to the question of whether anyone actually needs this particular technology for anything practical. The larger context here is that quantum computing is still in a very early stage. We don't have large-scale quantum computers. We don't have quantum computers that can solve real-world problems better than classical computers at any meaningful scale. Most quantum computers today are research devices. They're tools for scientists to study quantum physics and test quantum algorithms. They're not practical computing devices for solving business problems or scientific challenges. IBM's latest quantum processors have a few hundred qubits. Google's superconducting quantum processors are similar in scale. China has quantum systems with comparable specifications. But having a few hundred qubits is very different from having a useful quantum computer. The fundamental problem is quantum error rates. Quantum computers are incredibly noisy. A typical superconducting qubit might have a 2-qubit gate error rate around 1%. That means 1 out of every 100 operations fails or produces incorrect results. For classical computers, this would be catastrophic. But quantum computers are fragile in ways that classical computers aren't. When you run a quantum algorithm, you need to perform thousands or millions of quantum gates to solve a problem. If each gate has a 1% error rate, those errors accumulate. They interfere with each other. They produce wrong results. To fix this, you need quantum error correction. You need extra qubits dedicated to checking whether other qubits are correct. And you need many, many of them. Some estimates suggest you might need 1,000 physical qubits for every logical qubit you can rely on for computation. This is where quantum computing stands right now, not on the edge of revolution. In the early research phase, where we're still struggling with fundamental problems like error correction and scaling, when you see headlines about quantum computing breakthroughs, you need to ask very carefully whether this breakthrough actually moves us closer to solving those fundamental problems, or whether it's solving a theoretical problem in isolation. In the case of QRAM, the answer is actually yes. This is a case where a quantum research breakthrough does seem to move the field forward toward practical quantum computing. QRAM is something that many quantum algorithms actually need. Many quantum speedups assume that you can load classical data efficiently into a quantum computer. Without QRAM, or something like it, that assumption falls apart. So the fact that researchers have shown that you can build a QRAM system experimentally is genuinely valuable. It's not solving something nobody cares about. It's solving something that the field actually needs solved. But solving it in principle and solving it in practice are different stories. The fact that you can build a QRAM system with 81% fidelity in a laboratory with a small number of qubits doesn't tell you how hard it would be to build a QRAM system with 95% fidelity with 100,000 qubits. It might be trivial to scale. It might be impossibly hard. You don't know yet. The Zhejiang team certainly doesn't know yet. And the researchers were clear about all of this in their technical paper. They described the challenges. They outlined the limitations. They were responsible scientists talking about the actual state of their research. This is where the misinformation apparatus takes over. The technical paper is accurate. The research is solid. The scientists are honest about what they've accomplished and what remains to be done. But the headline writing apparatus doesn't care about accuracy. It cares about engagement. It cares about getting people to click. It cares about making the impossible sound imminent. And that's where the story transforms. That's where quantum memory defeating traditional RAM becomes the narrative. That's where your computer's about to change forever becomes the implication. That's where the truth gets mangled into something viral. The playbook is consistent across quantum computing breakthroughs. It has been for years. Someone announces a new qubit record. 50 qubits, 100 qubits, 300 qubits. Immediately, the discourse shifts to quantum computers replacing classical computers. Quantum computers solving problems that classical computers can't. The quantum revolution is here. Except quantum error rates are still terrible. Quantum algorithms that provide a genuine speed-up over classical approaches are still extremely rare. And scaling quantum computers to the point where they're practical for real-world problems is still decades away at minimum. But those are boring facts. Those don't trend on social media. Those don't generate engagement. So instead, you get headlines about quantum defeating classical, quantum replacing traditional technology, quantum revolutionizing computing right now. Each headline is technically referring to something real, but the real thing is buried under layers of hype and misinterpretation. By the time the headline reaches the public, the research has been transformed into something that bears no resemblance to what actually happened. This matters because it distorts how people think about quantum computing. It creates unrealistic expectations. It makes people think that quantum computers are about to become practical when we're still in the early research phase. It makes people believe that quantum will replace classical computing when the actual future is probably going to involve quantum and classical working together, each doing what it does best. And it creates a cycle where each new quantum research breakthrough is covered with sensationalism, because that's what generated engagement last time. The Zhejiang research is a good example of something that's genuinely important, but also genuinely preliminary. The team demonstrated that QRAM can be built. They showed that the bucket brigade architecture works in principle on superconducting qubits. This is valuable. This advances the field. But it's still a long way from practical QRAM systems that could be used in real quantum computers solving real problems. The fidelity numbers need to improve significantly. The scaling challenges need to be solved. The error correction problem needs to be addressed. And even after all of that is done, someone would still need to build an actual quantum computer large enough and capable enough to take advantage of QRAM and run a quantum algorithm that provides a meaningful advantage over classical approaches. We're not close to that yet. Not even close. And anyone claiming that this research means we're about to replace classical computing with quantum computing is either selling something or doesn't understand what they're talking about. The reality is more nuanced, more interesting, and more honest than the headline suggests. The reality is that quantum computing is progressing, that real advances are happening, that talented researchers are solving hard problems. But quantum computing is still years away from practical applications at meaningful scale. And QRAM is just one piece of a much larger puzzle that includes quantum error correction, quantum algorithms with genuine speedups, quantum hardware that's robust and scalable, and practical problems where quantum computing actually provides a better solution than the classical approaches we already have. The fact that researchers at Zhejiang University successfully demonstrated a QRAM architecture is genuinely impressive because they've shown that at least one piece of that puzzle can be built. But one solved piece doesn't mean the puzzle is complete. One demonstration of viability doesn't mean the technology is ready. One proof of concept doesn't mean the revolution is here. And a headline that says quantum memory defeated traditional RAM is technically referring to something real while being fundamentally misleading about what that something is. This is how misinformation works in quantum computing. Not through outright lies, but through selective truths. Through taking something real and focusing on the parts that are sensational while ignoring the parts that are complicated. Through letting the implication of a headline do the work that actual facts should be doing. And through relying on the fact that most people won't read past the headline anyway. Most people will see quantum defeats classical and move on, already having formed an impression that quantum computing is about to take over. They won't read the technical details. They won't understand the actual limitations. They won't see the caveat that this is still a proof of concept years away from practical deployment. This playbook has been running for years in quantum computing. Google announces a quantum chip with more qubits than before. Headline: Google achieves quantum advantage. The catch: the demonstration was narrow, specific to a problem quantum computers were essentially designed for, with no clear path to practical application. IBM announces improvements in quantum error rates. Headline: IBM quantum computer breakthrough. The context: error rates are still too high for practical computation. Researchers at MIT demonstrate a new quantum algorithm. Headline: new quantum algorithm could change computing forever. The reality: the algorithm works on a toy problem and requires error rates and scales we don't currently have. Each headline is technically accurate. Each one reports something real, but each one omits the context necessary to understand what that real thing actually means. The Zhejiang researchers didn't cause this misinformation. They did honest work and reported it honestly. They're scientists doing legitimate research in a field that needs more people doing legitimate research. The problem is in how that honest work gets packaged and presented to the world. The problem is that engagement and accuracy don't always align in the attention economy. The problem is that the sensational version spreads faster and further than the accurate version. And the problem is that people have been conditioned by years of quantum computing hype to accept extravagant claims as reasonable statements about imminent transformation. The real story here is much more interesting than the headline suggests. The real story is about how quantum computing is making progress, how researchers are solving specific problems that stand in the way of practical quantum computers, how QRAM is one of many tools that quantum computers might eventually need, how the path from laboratory demonstration to practical technology is long and uncertain, and how the process of scientific advancement is actually much more incremental and frustrating and real than the viral headlines would have you believe. That story is interesting because it's honest, because it acknowledges both the genuine progress and the genuine limitations, because it respects both the importance of quantum computing as a field and the caution required when evaluating where we actually are in developing it. The next time you see a headline about quantum computing defeating classical computing, defeating artificial intelligence, or defeating something else entirely, take a moment. Ask yourself whether the headline accurately captures what the research achieved or whether it's playing with implications and misunderstandings to generate engagement. Ask yourself whether you're reading a technical description of something genuinely important or whether you're reading marketing designed to look like news. Because that difference matters. That difference shapes how you think about the future of computing. That difference determines whether you have an accurate sense of where quantum computing actually is or whether you've been sold a story that feels true but doesn't match reality. In the case of the Zhejiang research, the accurate story is that quantum random access memory architecture was successfully demonstrated at proof of concept on a superconducting quantum processor, showing that one component that quantum computers might eventually need can actually be built. The inaccurate story is that quantum memory defeated traditional RAM, and your computer is about to change. Both stories reference the same research. One is true, one is false, and the false one is the one that's spread across the internet because that's what engagement looks like in an age where sensationalism travels faster than nuance and where a catchy headline matters more than actual understanding of what the research really means. The truth is more complex. The truth is more interesting. The truth is that quantum computing is making progress, genuine progress, but it's incremental progress on fundamental problems. The truth is that QRAM is a tool that quantum computers might eventually need, and showing that this tool can be built is valuable. But valuable in the lab doesn't mean valuable in the real world. Proof of concept doesn't mean practical deployment is imminent. Demonstrating that something works in principle doesn't tell you when or whether it will work at scale. And that's the story that should be told. That's the story that matters. That's what distinguishes real scientific communication from sensationalism wearing the mask of scientific progress.